All right, great. I'm going to try reading this section from the book, section 9.9 on the gaps between primes. Let me scroll through a little bit and see what is coming up. All right, so there's a little notation down here. I see some fractions, some names. Um, Looks like there's some words that are defined that are in italics. Ooh, there's a nice table. And oh, this looks like it's getting a little heavier. Some approximations, some natural logs. Ooh, that looks a little scary. Have to unpack all that when we get there. And oh, here we go. Almost to the end. And then there's the reference at the end. So this is a paper by Goldston, Pence, and Yildirim. Okay, so that's what? A little more than 3 pages? One, two full pages. A little more than 3 pages. Great. So let's see. The average distance between consecutive primes. Okay, so I can think of some consecutive primes like 3 and 5, or 23 and not 25, 27, 29. So I guess distance between 3 and 5 is 2, and 23 and 29 is 6. Okay, so we're thinking about what happens on average. Primes are natural numbers with exactly two divisors, like, okay, all those. Because all even numbers in greater than 2 have at least three divisors, right? Because they're even, 1 and 2 and the number. 2 is the only even prime number. Okay, that fits with what I thought about prime numbers before. So this implies that the pair 2, 3 is the only pair of consecutive prime numbers. But I thought we were trying to find the distance between consecutive prime numbers. Only pair of consecutive prime numbers. Okay, so maybe that means just one right after the other. I'm confused. Okay, so maybe we'll have to come back to consecutive because they're right next to each other. Maybe the other ones can't be. Okay, circle back. Pairs. Okay, P is 3 and Q is 5. So we're doing P's and Q's. Okay, maybe, oh, 5 and 7, 7 and, or 11 and 13. Okay, those are right next to each other. Well, almost right next to each other. They're two apart, two apart, and so on are examples of pairs of primes P and Q such that Q minus P is 2. Okay, end of the sentence is where P and Q shows up. Great. All right, I understand now. So those are some examples. Can I think of another example? So 23 and 29, that was further apart. So what's a bigger one of twin primes? So 51, no, 51 is not prime. 53 and 55, no, 55 is not prime. 59 and 61. Okay, so that's another example. I could try coming up with some more examples later, but this is saying that it's a conjecture. There are infinitely many of them. And this is one of the oldest unsolved problems in math. That's pretty cool. And a naive reason why this conjecture may be hard to prove is that if we study the sequence of prime numbers further and further, the average distance between consecutive primes becomes larger and larger. Okay. So if the average distance is getting bigger and bigger for whatever reason, then you wouldn't expect too many of them to end up very close together. So that's why it's hard. Right. Okay, right. So because if they weren't getting sort of on average further apart, then maybe it would be obvious that lots of them bunch up. So the famous prime number theorem states that for any n, there are about, Here we go with the logarithms. Okay. N over natural log of n primes less than n. Okay, so I could graph that. So maybe I'll take a moment and open up a graphing calculator and see what that function looks like. Because instead of n over log n, I could do x over log x and see what that looks like. I'll come back to that. Okay, but this is apparently a famous prime number theorem. So maybe that's something to look at more. Can do a little internet searching. So and the average distance is approximately the natural log of n. I'm not sure how that follows, but I'll roll with it. And then for n really big, how do you say that number? 10 to the 100. I'll have to Google that. This implies that the average distance between 100-digit primes is about 230. That's not so far apart. I guess this is how the logarithm kicks in. But that's still bigger than 2. Okay, so of course, this does not mean that this distance is exactly 230 in all cases, right? Because it's an average. For some pairs of consecutive primes, it's larger. For some pairs, it's smaller. Okay, so what do we got so far? We have some examples of consecutive, some examples of twin primes, and we have a conjecture that there are infinitely many of those pairs, but we should be sort of surprised by this because in general, primes spread out. Okay, so far so good. So we'll scroll a little bit. Oh, my face was probably in front of. Okay, very good. Uh, the pairs of primes at distance much lower than average. Great. So, on average, about the natural log of the the nth prime. The twin primes conjecture states that, okay, the ones that are next to each other, p n minus, okay, the nth one and the n plus first one. When you subtract them, you get 2. Um, but we're gonna not do that, but we're trying to show that it's less than average infinitely often. Well, I mean, unless it's exactly average all the time, but okay. We'd like to show that, okay, this distance is pretty small, really small number epsilon times the natural log, which makes number small when you plug it in for infinitely many values of n. Okay, and in 1926, Hardy and Littlewood proved this for not that small, but pretty small, 2/3, but they needed to assume something called the generalized Riemann hypothesis. And Erdos proved in later that it holds, but we don't know what it is. And in 1954, Ricci proved 15/16, and it got better. And okay. But now Goldstone, Pence, and Yildirim proved that there are infinitely many values of n such that what's their epsilon? Oh, for any epsilon. Oh, wow. So that means you can make it really small and do the logarithm. And okay, so that means that they're infinitely often, infinitely many values of n that the gap is really, really small, but not like the number too small, but a number that grows with the size of the prime numbers. So theorem 9.9 states that what asterisk? Oh, the wait, okay. They're all saying okay. Oh, the asterisk is the asterisk is oh, this thing here. Uh oh, this is like the name for this statement. Oh, when we don't, okay. And then you can make the statement different ways when all these different people did star. I didn't even notice the star for, oh, for different, you do the star statement, but for different values of epsilon. Okay. And then theorem, okay, the thing we're trying to understand, the big theorem from the section that star holds for any epsilon, no matter how small. Okay, I can see how this is better than these previous things that had particular fractions, but they were not real tiny fractions. They were, yeah, okay. For any, you can make the number as small as you want. In the author's words, there exist consecutive primes which are closer than any arbitrarily small multiple of the average spacing. So you have the average spacing, you say, oh, you can do a very, very small fraction of the average spacing and still get infinitely many primes that are that close. Well, theorem 9.9 is huge progress compared to the previous results. It is still far from confirming the twin primes conjecture. Okay. Okay. We made some progress. How far are we? I feel like we've been doing this for a while. Oh, we made it through about a page. Okay, and I'm still confused about, well, I don't know what I don't know what this generalized Riemann hypothesis is, and I don't know, I'm still confused about this consecutive business from earlier, and I'm not sure what this all has to do with logarithms. But okay. Let me start doing some more. I think I need to take a break. Maybe come back to it and try some examples. Maybe it would help if I plugged in some numbers for the logarithm. Oh, I was going to try plotting this graph. Yeah, maybe I'll take a break and then I'll look at that graph.